Hello, welcome back. Let's start chapter 4, I guess. Okay, chapter 4, Stoichiometry of Chemical Reactions. Quick word about chapter 4. Chapter 4 is a long chapter, and it's full of a lot of stuff. 3 and 4, I think, are probably the two most challenging chapters that you're going to encounter in Chem 1. Now, if you can make it through 3 and 4, you probably have the intellectual capacity to make it the rest of the way. So concentrate really hard on the stuff in Chapter 4, because everything you see in Chapter 4, you're going to see again in General Chemistry 2. And if you learn it now, you won't have to learn it when you get to General Chemistry 2, plus the new stuff. All right? So where do we start? Well, let's talk a little bit about chemical equations. Chemists are basically lazy by nature. We could write out, I went into the lab and I added this and it turned green, it fizzed, and so on and so forth. But, there's got to be a quicker way, right? That's what a chemical equation is. A chemical equation is a way to express what happens in a chemical reaction in kind of a shorthand method. All right, so for example, this is an example of a chemical equation. It looks something like that. So a few things here to notice about my little chemical equation. The first thing is I've got everything over here on the left-hand side. So that would be the H2 and the O2 there as well. Everything on the left-hand side of a chemical equation, these are called my reactants, because this is what I'm reacting. So that makes sense. So I have two reactants in this chemical equation. That would be H2 and O2. It's a generic term to talk about everything on the left-hand side. Everything on the right-hand side of the arrow, these are called my products, because this is what I'm producing. So in this case, I only have one product in this chemical reaction, and that would be H2O. All right? The little symbols here in the parentheses, what they do is they tell me what the state of matter that substance is in this particular reaction at that temperature. So for example, if you see an S after something, that means, well, it's a solid. If you see an L after something in a chemical equation, well, that means that's a liquid. If you see a G after something, that means it's a gas at that temperature. Now, if you see an AQ after something, what that stands for is that stands for aqueous. Aqueous means mixed up in water. So if I have things that are in solution, that's an aqueous reaction. Water is the solvent. A lot of reactions where water is the solvent, very important. Mostly what we will concern ourselves with are aqueous reactions in general chemistry. Of course, not everything goes into water, although a lot of things do. And so when you get to organic chemistry, then you start dealing with a lot of non-aqueous solutions, and then you start worrying about that. But most of the stuff that we're going to work with here in general chemistry are going to be mixed up in water. And so, yeah, you'll see a lot of aqueous solutions, as you go. All right? Well, if you'll notice my little chemical equation here, there's something wrong with my chemical equation. So what's wrong with my chemical equation? Well, it's not balanced. Well, what do we mean by that? I mean, it looks pretty straight to me. What do we mean by not balanced? Well, balanced means I have to have the same number and types of atoms on both sides. All right, notice over here I'm starting with 2 hydrogens. Here I've got 2 hydrogens. Well, that's okay, but I've got 2 oxygens over here and I only have 1 oxygen over here, and that's not good. Well, why is that not good? What's wrong with that? Am I breaking any law by doing that? Well, yes, actually I am. I'm breaking the law of conservation of mass, which says matter can neither be created nor destroyed. All right, I've started with 2 oxygens. When I'm done, I got to have 2 oxygens. If I don't have to, I can't have 3, I can't have 1, I can't have 4, I've got to have 2 and exactly 2, because matter just doesn't disappear. It also just doesn't pop out of the void. All right. So how many ever atoms of a particular element I have over here on the left-hand side, I have to have on the right-hand side. And if we do that, we say the equation is balanced. Okay, well, let's see. Let me just put a 2 here. We'll say H2 plus O2 goes to H2O2. Well, now I'm balanced, right? What's wrong with that? Well, if you do it that way, you are fundamentally changing what the equation's trying to say. You're saying hydrogen plus oxygen goes to H2O2, which is hydrogen peroxide. But that's not what I'm trying to say. I'm trying to say H2 plus O2 goes to water. All right, so how can I do that? Well, maybe I can put a big 2 right here in the middle of this formula. Can I do that? No. If I put a 2 in there, what does that mean? Well, it doesn't mean anything. It's just nonsense. All right, so you can't put a 2 here in the middle. You can't change a subscript. Never change a subscript because you're fundamentally changing what the equation is trying to say. So how can I say hydrogen gas reacts with oxygen gas to give me water, liquid water, and still get this equation to balance? Well, what we're going to do is we're going to put a 2 over here in front of the H2, and we're going to put a 2 over here in front of the H2O. All right, if I do that, how many hydrogens do I have on the left-hand side? Well, I've got 4 hydrogens. See, 2 H2s gives me 4 hydrogens. How many hydrogens do I have over here? Well, I've got 2 water molecules with 2 hydrogens apiece, so that's a total of 4 hydrogens there. So that's balanced. How many oxygens do I have over here? Well, I have an O2, which has 2 oxygens. How many oxygens do I have over here? Well, I've got 2 water molecules. Each one contains 1 apiece. So I've got a total of 2 oxygens there. And so this is what we call a balanced equation. And that's how you balance equations, by putting what we call coefficients, or numbers, out in front of formulas. Make sense? So what this is saying is 2 molecules of H2 will react with 1 molecule of O2 to produce 2 molecules of liquid water. Are we still saying hydrogen plus oxygen yields water? Yes, we're just specifying how much hydrogen and how much oxygen and how much water. All right, and that's called a balanced equation. So, how do you balance equations? That's kind of where we're headed. If you have taken high school chemistry, you probably have seen this before, because this is one thing they love to make you memorize the periodic table, and they love to make you balance equations in high school. Just, equation after equation after equation. So why do they do that? Well, because honestly, you haven't had enough math to do anything really very interesting yet. So that's what they do to you. All right. So for some of you, this is probably not going to be new material. But for some of you, it might be, or maybe you weren't paying attention in high school, maybe when you should have been. So maybe we need to go over it again. All right? So when you're balancing an equation, you must have the same number of atoms of each type on both sides. And you achieve this by adjusting what we call coefficients in front of formulas. That's these numbers up here. Okay? Now, when you're doing coefficients, there's 3 things you can do. All right? The first thing you can do is you can put a coefficient on one side or the other in front of something. The second thing that you can do is you can add 2 coefficients. You can add a coefficient to the left-hand side and a coefficient to something on the right-hand side. Sometimes you have to do that. We'll talk about it. The third thing you can do is you can adjust a coefficient. Now, when you're adjusting coefficients, it's usually better to go up and not down. If you go down, you end up messing more stuff up than if you tend to go up. So that's kind of what I would do. But that's it. Those are the only 3 things you're allowed to do. All right? Well, what I've provided for you here is a little checklist, or a little series of steps for balancing an equation. Balancing an equation is like any new thing you do. When you first do something new, it's nice to have some sort of a stepwise procedure that you can follow. After a while, you don't need the procedure anymore. Maybe you find shortcuts to the procedure even. But if you haven't done it much, having a series of steps to kind of get you there is really nice. So that's what I'm going to provide for you. So I'm going to provide for you a series of steps that you can follow. Eventually, you may get to the point where you can think 2 or 3 steps ahead, or you might find your own little method. But if you have nothing, this is a really good place to start. All right. So here is a general method for balancing an equation. So the first thing you're going to do is you're going to pick an element, any element. Usually I pick the first one in the formula, in the equation, because you're going to go to the second, the third, and the fourth, and that way you don't accidentally skip something. So I just usually kind of go in order. All right. Once you pick that element, you're going to balance that element by adding a coefficient to either one side of the equation or both sides. All right. Once you get that one balanced, you're going to pick another element, and you're going to balance that. What if, when you balance that element, you mess something up? Is that okay? Yeah, it's okay. Sometimes, you got to crack a few eggs to make an omelet here. Do I go back and fix it right away? No. Just continue forward. All right? We're going to loop back around. We're going to take care of it eventually. But just keep going forward. Don't worry about it. Okay? So you're going to get that one balanced. All right? Then you're going to go to the third element. You're going to balance that. And the fourth element, balance that. And you're going to keep going until all your elements have at least been attempted once. Okay? Once you do that, you're going to loop back up here to step 1, and you're going to look at that first element. If it's messed up, you're going to fix it. If it's not messed up, you're going to leave it alone. Don't fix things that aren't broken. All right? Then you're going to go to the second element, and then the third element, and so on and so forth. Okay? And then you go through it. If you loop through and you don't have to change anything, then you have yourself a balanced equation. You're done. If you have to change anything, the first, the second, the third, the fourth, whatever, then what you're going to do is you're going to loop back around when you get through, and you're going to start the first element, and you're going to do the same thing again. So what it feels like sometimes, it feels like you're just kind of going in circles here. Okay, and that does happen sometimes. Some of these come out really easy, but not everything comes out easy in life. That's just kind of the way it works. All right? However, I will say this. If you're balancing equations and you get up to something like 47 oxygens on one side and 36 oxygens on the other, and 152 phosphorus atoms over here, and 47 phosphorus atoms over there, and you've used up a full page, you've probably messed up. Does that happen? Is it possible? Yeah, it's possible. Is that going to happen here? No, it's not. So probably what you've done is you've made a mistake somewhere along the way. Now you can go back through that entire page and try to find your mistake. But here's the thing about looking for mistakes. If you go through an entire page and you look for a mistake, you're going to keep overlooking it every single time. They're hard to find. So sometimes the best thing to do is just crumple up that sheet of paper and start over and get yourself a fresh perspective. And hopefully the second time you go through it, you won't make the same mistake. All right, so they don't come out always on the first try. But if you're finding you're using an entire page of paper to do it, I'm probably not going to throw anything like that at you. Try starting over and see if it comes out a little bit easier. All right, well, let's go through a few here. And I've got a little special something for you. So let's start here, I guess, first. So the combustion of propane and air to give carbon dioxide and water. So see if you can write the equation for this first, and then let's see if you can balance it. All right. Well, propane is an organic compound. They have their own special nomenclature. And so that's C3H8. You find this in like the little white tanks for a gas grill, something like that. That's propane, actually. All right. Well, I can burn propane. And so when I burn something, what does that mean? Well, that means combining with oxygen. We'll find oxygen is O2 in the atmosphere. And what I get carbon dioxide. What's the formula for carbon dioxide? That's CO2. And then water, of course, would be H2O. So this, in chemical equation form, would be this. C3H8 plus O2 goes to CO2 plus H2O. Okay? All right. Well, is my equation balanced? What does that mean? That means, do I have the same number of type of atoms on both sides? Well, no, I don't. My carbons are messed up, my hydrogens are messed up, my oxygens are messed up too. So this definitely is not a balanced equation. Okay, is there any way I can get this thing balanced? Sure. All right. So let's go back to our little step method. So the first thing we're going to do is we're going to pick an element. So let's just start here with carbon. Okay, so how many carbons do I have on the left-hand side? Well, I got 3. I got one propane molecule with 3 carbons, so 3 over here. How many do I have on the right-hand side? Well, I just have 1. Okay, is there any way I can get 3 carbons on both sides? Yeah, what I can do is I can put a 3 in front of the CO2. 3 CO2s gives me 3 carbons, which balances this 3 carbons over here. Okay? Now, when I'm going through this, what I'm going to do is I'm going to rewrite the equation every single time I mess with a coefficient. Do you have to do that? No. I do this so that you can tell exactly what we did in the last step. You know, if I showed you an equation and then just showed you the equation balanced, well, that doesn't really help matters, does it? So I'm going to rewrite it every time I change. You don't have to do that. If you're me, I just put a 3 right here, and then I'd work with this equation when I balance the next one, and then keep doing it. You know, if it starts getting messy, then what you can do is just rewrite the equation where you are down here and start working with that. All right, but yeah, you don't have to rewrite it every single time like I'm doing here. Okay, just strictly for your notes. All right. Okay, so we got the carbons balanced. So what's next? Well, we're going to pick another element. Well, how about the hydrogen? Okay, so how many hydrogens do I have on the left-hand side here where my reactants are? Well, I have 8. How many hydrogens over here? Well, only 2. See, 1 water molecule with 2 hydrogens. How can I get the same number on both sides? Well, I can put a 4 in front of the H2O. See, if I have 4 water molecules, each with 2 hydrogens apiece, I have 8 hydrogens. The same as over here. Make sense? Okay. Third element, we got oxygen. Okay, how many oxygens over here? Well, I have 2. How many do I have over here? Does everybody see 10? Where'd we get the 10 from? Well, I've got 3 CO2s, each contains 2. 3 of them would be a total of 6, right? 6 oxygens. And I've got 4 water molecules over here, each contains 1. So that's a total of 4. What's 6 and 4? Well, that'd be 10. So everybody see 10 oxygens over here? 2 over here. How can I fix that? Well, I can put a 5 in front of the O2. 5 O2s gives me a total of 10 oxygens over here and 10 oxygens over here. All right, so we've gone through every element. Are we done? Maybe. What do we do next? Well, you're going to loop all the way back up to the first element again. You're going to check it. All right, so we're going to go back to the carbons. How many carbons? 3. How many over here? 3. How many hydrogens? 8. How many hydrogens over here? 8. How many oxygens? 10. How many oxygens? 10. Notice that we went through every single element again. Did we change anything in that round? No. And so therefore, there you go. There's your balanced equation. And so this says 1 molecule of C3H8 will react with 5 molecules of oxygen to produce 3 molecules of CO2 and 4 molecules of water. If you saw that written out, you should be able to write the equation. If I wrote you the equation, you should be able to write that out, because that's what it means. Make sense? Okay. Well, as I said, you know, one example is probably not enough. You know, to really get good at this, you just got to practice. So to practice, you've got to have problems to work, right? So you might be asking yourself, is there a bunch of equations I could balance so I could get really, really good at this? Well, that's a really nice question. Turns out there is. If you will look in your notes, what I've got for you here is I actually have a sheet of equations for you to balance. Okay? When are these due? Well, they're not. Okay? This is totally up to you. So this is for you to practice on. You know, you can do as many or as few as you want. If you want to do them all, do them all. If you want to do one of them, do one of them. If you don't want to do any of them, if you feel like I'm really good at balanced equations and I don't need the help at all, fine, don't do it. You know, you paid your tuition. It's your money. So that's okay by me. You know, whatever you want to do. But if you want to practice, here's plenty of stuff that you can practice on. All right. And so what we've got for you here is we've got 35 equations for you to work on. So yeah, lots and lots for you to practice. How do you know if you got it right? Well, if you have the same number and types of each atom on both sides, I guess you got it right. If you don't have the same number and types of each atom on both sides, I guess you got it wrong. So that's a really good way to check yourself. Okay, well, let's do a couple from this little page here and see if we can get fairly decent at it. I am going to, I'm going to skip this one for now. Let's go to 23 first, and then we'll come back and do number 3. Okay. All right, 23. Do you remember that I said, and that's 23 over here in, there we go. Your little handout if you haven't printed that already. So you remember I said that there are times when you have to add coefficients to both sides. So when would be a time? Well, that would kind of be here. So let's look at this one. It's a good example. So this one first, then we'll come back and pick up this one. So I've got, this is aluminum bromide. Okay, no Roman numeral because it's aluminum. Remember, always plus 3. Aluminum bromide plus chlorine goes to aluminum chloride plus bromine. All right, so is my equation balanced? No, I don't have the same number and type of atoms on both sides, so it's not balanced. Okay, so where are we going to start? Well, let's start with the aluminum. How many aluminums over here? 1. How many aluminums over here? 1. Okay, so what do I need to do? Well, nothing. It's not broken. Don't fix it. Just leave it alone. Move on to the second one. How many bromines do I have on this left-hand side? Well, I've got 3. How many bromines do I have over here on the right-hand side? Well, I've only got 2. Is there any way to get 3 bromines over here on the left-hand side? Right-hand side, excuse me. No. See, because if I put a 2 in front of the Br2, that gives me 4. Is there any way to get an odd number of bromines over here without using fractions? No. All right, so here's a case where I'm going to have to use coefficients on both sides of the equation. When you do this, what you're looking for is you're looking for a set of coefficients that gives you the least number of bromines, in this case, on both sides that you can. All right. The reason why you want to do that is because if you don't get the least number, the numbers start getting really, really large, and you'll end up with like 25 bromines over here and 45 bromines over there, and the math gets really cumbersome. So you want to keep the numbers down as much as you can. If you don't get the least number on both sides, sometimes the problem just fixes itself. If it doesn't fix itself, what will happen is you'll end up with coefficients here that are multiples of something. So this will be like a 2, a 4, an 8, and a 2. You know, if that happens, if everything's divisible by the same number, like 2, just divide everything by 2. So there'd be a 1, a 4, what we say, 2, we said 2, 4, 8, right? So a 1, a 2, a 4, and then a 1, because that was a 2. See, we just divide everything by 2. So it's an easily fixable thing, but it just gets cumbersome when you're balancing. So it's better if you can keep the numbers down somehow. Okay? All right, so what's the smallest number of bromines that I can get on both sides? Well, I can put a 2 over here in front of the AlBr3. How many bromines does that give me? That gives me 6. And I can put a 3 over here in front of this Br2. And that gives me 6. And so 6 is the smallest number I can get on both sides. And here's a case where I have to add coefficients to both sides. And that happens occasionally. You know, especially in a situation like this where there's no way you can get an odd number over here. There's, you know, no way, well, you could get an even number over here, but you couldn't get those balanced without putting 2 coefficients there. Okay? All right, well, that takes care of the bromines. How many chlorines do I have over here? Well, I have 2. How many chlorines do I have over here? Well, I have 3. So we've got the same situation here. So how are we going to fix that? Well, we're going to put a 3 in front of the Cl2. And we're going to put what looks like a very ugly 2, which is what that is, in front of the AlCl3. Okay? That gives me 6 chlorines over here. And then 2 AlCl3s gives me 6 chlorines over here. All right, so we've gone through all the elements. What do? Go back to step 1. So we're going to look at the aluminums. How many aluminums over here? Well, I have 2. How many aluminums do I have over here? I have 2. How many bromines? 6. 6. How many chlorines? 6. 6. We've gone through everything again. We didn't have to change anything in that round. Balanced equation. There you go. Can you do it? Okay. Well, you'll remember I said that if you do this enough, after a while you start to find shortcuts. It's like anything that you do. Like if you're a chess player or something, you play enough chess, it's like, oh yeah, I recognize this position. I moved this bishop over here last time, and that didn't work out real well for me. Maybe I moved my knight instead. But if you haven't had the experience, of course you wouldn't know that, right? So here's a little shortcut that you can use sometimes to make your life a little bit easier when you're balancing equations. If you see a polyatomic ion, of course you know your polyatomic ions because you studied that for the last test. If you see a polyatomic ion on one side and it's still together on the other side, what you can do is you can balance it usually like it's one big giant atom. So if I see carbonates on the left-hand side of the equation and I see carbonates on the right-hand side of the equation, I can balance my carbonates. All right, and that works pretty well. All right, the large majority of the time. Now, if I see a polyatomic ion on one side of the equation and it's not together on the other side, you have to balance those as individual atoms. All right, things like that work really well. Okay, this one, 16 here. See, here's a sulfate over here, here's a sulfate over here, here's a hydroxide over here, and here's a hydroxide over here. So if I balanced my sulfates and pretended like they were one big atom, this one actually comes out pretty easy. If you broke everything down as oxygen atoms, look how many oxygen atoms you're going to have over here and how many you're going to have over there. It can be done. It's just a little bit more cumbersome. All right. So that's a shortcut that you can use. I'm not going to do 16. I'm going to do one that's a little bit trickier than 16 for you. And I believe it's number 3. So let's take a look at our notes here. Okay. So that's this one right here. So let's take a look at number 3. And see how that goes. So this is zinc 2 hydroxide, or zinc hydroxide. Remember, zinc was one of those special exceptions that we didn't have to use the Roman numeral for. Plus H3PO4 in a water solution, that's phosphoric acid. Okay? And that leads me to zinc phosphate, or zinc 2 phosphate, if you call it that, I wouldn't take off, plus H2O. Okay? All right, so where do we start? Well, let's start with the zincs. Okay, so how many zincs do I have over here? Well, I have 1. How many zincs do I have over here? Well, I have 3. Okay, so how can I fix my zincs here? Well, I can put a 3 in front of the zinc hydroxide. And that gives me 3 zincs here, 3 zincs here. Ignore this right here. It's nothing. Just pay no attention. All right? Okay. What's next? Well, I've got a hydroxide over here. Do I see a hydroxide over here? No, I don't. So what that means is I'm going to have to balance these oxygens and these hydrogens separately. Okay? Do you see this PO4 over here? What's a PO4? What's a phosphate polyatomic ion you're supposed to know, right? Do you see any phosphates over here? Well, here's a phosphate. So I can't balance my hydroxides because they're not over here. But I have phosphate here and phosphate here, so we're going to pretend like that phosphate is one big giant element, and we're going to balance our phosphates. Okay? So, how many oxygens do I have on the left-hand side that are not in a phosphate? Is it 2? Is it 1? Is it 6? Is it 12? What's 6? See, each hydroxide contains 1 oxygen, but I've got 2 hydroxides, so that's 2 oxygens there. But I have 3 of these zinc hydroxides. 3 times 2 is 6. Does everybody see 6 oxygens over here? Okay. How can I get 6? How many oxygens do I have over here that are not in a phosphate? Well, I have 1. So how can I fix that? Well, I can put a 6 in front of the H2O. 6 H2Os gives me 6 oxygens here, 6 oxygens here. So we fixed it. Okay? How many hydrogens do I have on the left-hand side? Is it 6? Is it 5? Is it 9? 9. Where are my 9 hydrogens? Well, I've got 1 hydrogen and a hydroxide, and I have 2 hydroxides. So there's 2. but I have 3 of these zinc hydroxides. See, the 3 counts for everything here. So that's a total of 6 hydrogens here. But I've also got these 3 here, and 6 and 3 is 9, right? How many hydrogens do I have over here? Well, I have 12. I have 6 water molecules, each containing 2 hydrogens apiece. So 9 over here, 12 over here. How do I get the same number on both sides? Well, I can put a 2 in front of this H3PO4. Now, if I do that, that gives me 6 hydrogens here, and that gives me 6 hydrogens here. What's 6 plus 6? Well, that's 12. All right. Now, notice I could have fixed my hydrogens by adjusting this coefficient over here. Why did I put the 2 here? Well, because when I did, I not only fixed the hydrogens, I also fixed the phosphates at the same time. See, if you do this enough, eventually you can actually start looking ahead. Okay? But if you've not done it before, you can't do that. Okay? Again, it's a lot like chess. You know, if you just barely know how the pieces move, you're good just looking 1 move ahead at a time. But there are people that can look 3 and 4 and 5 moves ahead and know where everything's going to go. And that just takes experience, and practice, and a little bit of brain power. But, the rest of us over here, we're doing good if we just remember how the pieces move, right? All right. But that's why we want to put the 2 here. Okay? So that's 6 hydrogens here, 6 hydrogens here, 12 hydrogens here, 12 hydrogens here. Everybody good? Okay. All right. Now we're going to balance our phosphates. How many phosphates do I have over here? Well, I have 2 phosphates. Each H3PO4 contains 1, so there's 2 there. How many phosphates do I have here? Well, this zinc phosphate contains 2, so I've got 2 over here. So notice we fixed the phosphates there. Okay, are we done? Not yet. Got to loop back. So loop back, first element, look at the zincs. How many zincs over here? 3. 3. How many oxygens not in a phosphate? 6. 6. How many hydrogens over here? Well, there's 6 here, and there's 6 more here for a total of 12. 12 hydrogens here. And then how many phosphates? 2 here, 2 here. Notice in that round, we went through everything again. We didn't change anything along the way. Balanced equation. So say if you just kind of attack it systematically and just keep going, eventually you'll get to the correct answer. What you don't want to do is just start balancing things willy-nilly all over the place, because if you're nervous and you're on a test, you're going to skip something accidentally. But if you kind of approach it in a nice systematic fashion, it keeps your mind kind of calmed down a little bit, and hopefully you can get this. Okay? All right, you want to see one more? All right, last one. You want to see one a little harder? All right, let's try one a little harder. Here we go. This is 26 on your sheet. I'm going to look at that. So this is BCl3. What do we call BCl3? That's boron trichloride. Remember naming compounds. Hope you got that right. All right. What else we got here? We got P4. This is phosphorus. This is actually probably white phosphorus. White phosphorus is kind of found in a molecular form. Is a P4 little tetrahedron. 4 little atoms joined in a tetrahedron. Yeah, we'll talk about it. The other one is red phosphorus. What color is red phosphorus? Yeah, kind of red. And it's formed in kind of a network covalent type structure. Red phosphorus is kind of poisonous and kind of flammable. White phosphorus is extremely poisonous and extremely flammable. You don't want to deal with this stuff. Okay. I can react that with hydrogen, which of course we know is kind of flammable. When we get done, we end up with boron monophosphide. Here, it's not a phosphate because it's not a PO4. And I also end up with HCl. As the gas, this is hydrogen chloride. If I put this in a water solution, what would that be? That'd be hydrochloric acid. Okay, but in this case, we don't have any water, so it's just hydrogen chloride gas. All right, can you balance this equation? Well, let's try. Okay, so where are we going to start? Well, let's start with borons, I guess. So how many borons over here? 1. How many borons over here? 1. No problem. Let's move on. How many chlorines? 3. How many chlorines over, let's look at this here. How many chlorines over here? 1. How can I fix that? Well, I can put a 3 over here in front of the HCl. And that gives me 3 chlorines over here and 3 chlorines over here. Okay? Next one, phosphorus atoms. How many phosphorus atoms do I have on the left-hand side? Well, I've got 4. How many do I have over here? I only have 1. How can I fix that? Well, I can put a 4 in front of the BP. See, 4 BPs gives me 4 phosphorus atoms here, 4 there. But when I did that, I messed up the borons. Is that okay? Yeah, that's okay. Don't worry about it. Do I need to go back and fix them right away? No. Just keep moving forward. We'll catch it on the next round. See, and sometimes the problem just fixes itself, and you don't even have to mess with it. Sometimes when you ignore problems, they go away. Is that the way it usually works? Not usually, but sometimes it does. Rarely. But it's okay. We'll fix it on the next time around. So don't just be skipping willy-nilly trying to fix everything. Stuff's just going to get broken as we go. It's not that big a deal. Just keep moving forward. All right? Okay, so if we took care of the phosphorus atoms, what's next? Well, we've got hydrogen. How many hydrogens do I have over here? Well, I have 2. How many hydrogens do I have over here? Well, I have 3. Is there any way to get 3 hydrogens over here on the left-hand side? No. Because see, if I put a 2 there, that gives me 4. All right? So we ask ourselves, what's the least number of hydrogens you can get on both sides here by either adding coefficients or adjusting coefficients? And again, generally you mess up less things going up than down. So try to go up and not down. Do you see 6? Can you do less than 6? You actually can do less than 6. So how do I do less than 6? Well, you put a 2 here, so that gives me 4 hydrogens here, and we're going to take this 3 and we're going to change it to a 4. So 4 hydrogens here and 4 hydrogens here. All right? Now, what if you did do 6? Maybe you didn't see the 4. Is it a fatal mistake? Again, no. In this case, it actually fixes itself, and you probably would never even know that you didn't get the least number on both sides. If it's a mistake that you have to deal with, then again, you'll get multiples of everything, and you can start dividing by 2 or 4 or whatever, and you can fix it at the very end. So it's not a fatal mistake. You just would prefer to do the least number. So 4 is actually the least number here. Change the 3 to a 4, put a 2 in front of the H2. Okay? All right. Well, what's next? Well, we've gone through everything once, so we're going to go back around. So we're going to go back to the borons. How many borons here? 1. How many borons here? 4. Okay, so we messed up our borons. So how are we going to fix that? Well, we're going to put a 4 in front of the BCl3. 4 BCl3s gives me 4 borons. 4 borons. Okay? But when we did that, we messed up our chlorines. So, okay, we'll fix our chlorines. How many chlorines do I have over here on the left-hand side? Well, I have 12. So each BCl3 contains 3, and I have 4 of these, so it's a total of 12 chlorines. How can I get 12 chlorines over here on the right-hand side? Well, what we can do is we can add, we can change this 4 to a 12. I think I skipped a step there. We can change that 4 to a 12. 12 HCl's, each one containing 1, gives me a total of 12 chlorines. See? So 12 over here, 12 over here. Okay? How many phosphorus atoms? 4. How many phosphorus atoms? 4. Okay? How many hydrogens down here? When I change that to a 12. How many hydrogens? I guess we're here. How many hydrogens? Well, I have 4 over here, and I have 12 hydrogens over here. Here we are. So how do I get the same number on both sides? Well, I'm going to take this 2, I'm going to change that to a 6. That's the underline. And if I do that, I get 12 hydrogens here, 12 hydrogens here. Okay? Now, notice in that round we changed something. So what does that mean we have to do? Well, we have to circle back and go back to the first one. So how many borons? 4. 4. How many chlorines? 12. 12. How many phosphorus? 4. 4. And how many hydrogens? 12. 12. Notice in that round we didn't fix anything. Everything was fine. And that's how we know we're done. So you see, you just kind of start going in circles, but eventually, hopefully, you will get out of that circle, and you'll end up with a balanced equation. And so that's a nice little stepwise method for doing this. You might find shortcuts, you might not. I don't know. But it's certainly a good place to start. Can you balance equations? If you can't balance equations, you're not going to be able to do what we're going to talk about next time. So everything kind of builds here. You need to be able to balance an equation. So what does this equation mean? Well, this equation means 4 molecules of BCl3 will react with 1 molecule of P4 and 6 molecules of H2 to produce 4 molecules of BP and 12 molecules of HCl. And that's how it works. All right? Okay. Last thing here, hypothetically, let's say I had 6.022 times 10 to the 23rd molecules of P4 here. How many molecules of BCl3 do you think would react with that? Well, for every one of these, 4 of these react, right? What if I had 2 of these? I guess 8 of these would react. If I had 3 of these, and 12 of these react. See, it's always 4 times as many, right? So if I had 6.022 times 10 to the 23rd molecules of P4, how many molecules of BCl3 would react with that? Well, 4 times 6.022 times 10 to the 23rd. 4 times as many. Make sense? You may not understand where I'm going with this, but does it make sense? All right. If one of these reacts with 6 of these hydrogens here, if I had 6.022 times 10 to the 23rd of these, how many hydrogen molecules would react? Well, 6 times 6.022 times 10 to the 23rd. And 4 times 6.022 times 10 to the 23rd of these would be formed, and 12 times 6.022 times 10 to the 23rd HCl's would be formed, because for every one of these that reacts, I get 12 times as many HCl's. All right, think about that for a second. Does that make sense? Okay, but 6.022 times 10 to the 23rd molecules of P4 is equal to how many moles of P4? Well, that's 1 mole of P4, because that's what a mole means, is 6.022 times 10 to the 23rd of anything, right? What is 4 times 6.022 times 10 to the 23rd molecules of BCl3? Well, that's 4 moles of BCl3. 6 times 6.022 times 10 to the 23rd. Well, that's 6 moles of hydrogen. So, this equation actually means 2 things. Number 1, it tells me molecule to molecule ratios. But here's what else this equation tells me as well. 4 moles of BCl3 will react with 1 mole of P4 and 6 moles of H2 to produce 4 moles of BP and 12 moles of HCl. I got taken off this there. All right. So the moral of the story is coefficients in a balanced equation are not only molecule to molecule ratios, they're also mole to mole ratios. And that is going to become very, very important later on in the chapter. Okay? All right. If I gave you an equation, could you tell me what it meant? If I gave you a statement, could you write me an equation? If I gave you an equation, could you tell me if it was balanced or not? If it's not balanced, could you balance it? If you can do that, that's kind of what we're looking for. And we're ready to move on to Roman numeral number 2. All right? But that's a good solid 45 minutes worth of stuff. So I guess that's a good place to stop. So we'll quit there for now, and we'll pick up with Roman numeral 2 in our second video. So I guess bye for now.